learning objectives. In this chapter, the user would learn the following in detail: discrete time signals, discrete time systems, analysis of discrete time LTA systems, discrete time systems described by differential equations, implementation of discrete time systems, correlation of discrete time systems. Introduction: discrete time signals and system. The discrete time signals are introduced in this chapter and are used as basic functions or building blocks to describe more complex signals. The major emphasis in this chapter is the characterization of discrete time systems in general and the class of linear time invariant LTA systems in particular. A number of important time domain properties of LTA systems are defined and developed, and an important formula called the convolution formula is derived, which allows us to determine the output of an LTA system to any given arbitrary input signal. Difference equations are introduced as an alternative method for describing the input-output relationship of an LTA system, and in addition, recursive and non-recursive realizations of LTA systems are treated. The autocorrelation and cross-correlation of signals are defined and their properties are presented. Analysis of discrete time LTA systems. Linear shift invariant systems. Linear time invariant LTI systems are characterized in the time domain simply by their response to a unit sample sequence. The general form of the expression that relates the unit sample response of the system and the arbitrary input signal to the output signal, called the convolution sum or the convolution formula, is also derived. Thus, we are able to determine the output of any linear time invariant system to any arbitrary input signal. Techniques for the analysis of linear systems. There are two basic methods of analyzing the behavior or response of the linear system to a given input signal. One method is based on the direct solution of the input-output equation for the system, which in general has the form y of n equal to f of y of n minus 1, y of n minus 2, etc. y of n minus capital N, x of n minus 1, x of n minus 2, etc. x of n minus capital M, where f of dot denotes function of the quantities in brackets. Specifically, for an LTA system, the general form of input-output relationship is y of n equal to minus summation k equal to 1 to capital N a k y of n minus k plus summation k equal to 0 to m b k x of n minus k, where ak and bk are constant parameters that specify the system and are independent of x of n and y of n. The input-output relationship is called a difference equation and represents one way to characterize the behavior of a discrete time LTA system. The second method for analyzing the behavior of a linear system to a given input signal is first to decompose or resolve the input signal into a sum of elementary signals. The elementary signals are selected so that the response of the system to each signal component is easily determined. Then, using the linearity property of the system, the responses of the elementary signals are added to obtain the total response of the system to the given input signal. To elaborate, suppose that the input signal x of n is resolved into a weighted sum of elementary signal components xk of n, so that x of n equal to summation k ck xk of n, where the ck are the set of amplitudes in the decomposition of the signal x of n. If the response of the system to the elementary signal component xk of n is yk of n, thus yk of n equal to t of xk of n. Assuming that the system is relaxed and that the response to ck xk of n is ck yk of n as a consequence of the scaling property of the linear system. Finally, the total response to the input x of n is y of n equal to t of x of n equal to t of summation k ck xk of n equal to summation ck t of xk of n equal to summation k ck yk of n. Resolution of a discrete time signal into impulses. To resolve an arbitrary signal x of n into a sum of unit sample sequences, the elementary signal xk of n is selected as xk of n equal to infinity of n minus k, where k represents the delay of unit sample sequence to handle an arbitrary signal x of n that may have non-zero values over an infinite duration. The set of unit impulses must also be infinite to encompass the infinite number of delays. Now we multiply the sequences x of n and infinity of n minus k, since infinity of n minus k is 0 everywhere except at n equal to k, where its value is unity. The result of this multiplication is another sequence that is 0 everywhere except at n equal to k, where its value is x of k. Thus below is a sequence that is 0 everywhere except n equal to k, where the value is x of k. X of n into infinity of n minus k equal to x of k into infinity of n minus k. Consequently, if we repeat this multiplication over all possible delays minus infinity less than k less than infinity and sum of all the product sequences, the result will be a sequence equal to the sequence x of n, that is x of n equal to summation k equal to minus infinity to plus infinity x of k into delta of n minus k. The following are the graphical representation of the multiplication of a signal x of n with a shifted unit sample sequence, where the y-axis of the figure A, B and C are x of n delta of n minus k and x of k into delta of n minus k respectively, and the x-axis is given by n. Figure multiplication of a signal x of n with a shifted unit sample sequence. Response of LTI systems to arbitrary inputs, the convolution sum. The process of computing the convolution between input signal x of k and impulse response h of k involves the following 4 steps. Number 1. Folding. Fold h of k about k equal to 0 to obtain h of minus k. Number 2. Shifting. Shift h of minus k by n naught to the right within the bracket left if n naught is positive within the bracket negative to obtain h of n naught minus k. Number 3. Multiplication. Multiply x of k by h of n naught minus k to obtain the product sequence. V n naught of k equal to x of k into h of n naught minus k. Number 4. Summation. Sum all the values of the product sequence V n naught of k to obtain the value of the output at time n equal to n naught. For evaluating the response of the system over all time instance minus infinity less than n less than infinity, steps 2 through 4 must be repeated for all possible time shifts. Let us denote the response y of n comma k of the system to the input unit sample sequence at n equal to k by the special symbol h of n comma k minus infinity less than k less than infinity, that is y of n comma k equal to h of n comma k equal to t of infinity of n minus k. N is the time index and k is a parameter showing the location of the input impulse. If the impulse at the input is scaled by an amount ck equal to x of k, the response of the system is scaled output ck of h of n comma k equal to x of k into h of n comma k. Input is the arbitrary signal x of n that is expressed as the sum of weighted impulses, that is x of n equal to summation k equal to minus infinity to x of k into infinity of n minus k. Then the response of the system to x of n is a corresponding sum of weighted outputs, that is y of n equal to t of x of n equal to t of summation k equal to minus infinity to plus infinity x of k into delta of n minus k equal to summation k equal to minus infinity to plus infinity x of k into t of delta of n minus k equal to summation k equal to minus infinity to plus infinity x of k into h of n comma k. Above equation follows the superposition property of linear systems and is known as the superposition summation. If the response of the LTI system to the unit sample sequence infinity of n is denoted as h of n, that is h of n equal to t of infinity of n, then by the time invariance property, the response of the system to the delayed unit sample sequence infinity of n minus k is h of n minus k equal to t of infinity of n minus k. Consequently, the formula reduces to y of n equal to summation k equal to minus infinity to plus infinity x of k into h of n minus k. The formula gives the response y of n of the LTI system as a function of the input signal x of n and the unit sample impulse response h of n is called a convolution sum. In figure A, the signals used are h of k and x of k. In figure B, the signal gets folded. The folded signal is multiplied to the signal x of k, producing a product sequence and becomes h of minus k and v naught of k respectively. In figure C, h of minus k is shifted, becomes h of 1 minus k. Product sequence is then converted to v1 of k. In figure D, h of minus 1 minus k is generated by convolution and v minus 1 of k is generated by convolution. A graphical computation of convolution. Convolution operation is commutative. It is irrelevant which of two sequences is folded and shifted. Let us make a change in variable of summation from k to m by defining a new index m equal to n minus k. Then k equal to n minus m becomes y of n equal to summation m equal to minus infinity to infinity x of n minus m into h of m. Since m is dummy index, we can replace m by k so that y of n equal to summation k equal to minus infinity to infinity x of n minus k into h of k. Product sequences are defined as vn of k equal to x of k into h of n minus k. Wn of k equal to x of n minus k into h of k. Vn of k is equal to Wn of n minus k, and therefore y of n equal to summation k equal to minus infinity to infinity Vn of k equal to summation k equal to minus infinity to infinity Wn of n minus k. Since both sequences contain the same sample values in a different arrangement. Properties of convolution and the interconnection of LTI systems. In this section, we shall investigate some important properties of convolution and interpret these properties in terms of interconnecting linear time invariant systems. Commutative law. The asterisk symbol star is used to denote the convolution property. Y of n equal to x of n is convoluted with h of n equal to summation k equal to minus infinity to plus infinity x of k into h of n minus k. The impulse response h of n is folded and shifted. Y of n equal to h of n is convoluted with x of n equal to summation k equal to minus infinity to plus infinity h of k into x of n minus k. We may interpret this form of convolution formula as resulting from an interchange of the roles of x of n and h of n. The property embodied in above equation is called commutative law. X of n is convoluted with h of n equal to h of n is convoluted with x of n. Interpretation of the commutative property of convolution. Associative law. In many places we using star. That means star is the meaning of convolution. X of n star h1 of n star h2 of n equal to x of n star h1 of n star h2 of n is called equation number 1, where x of n tends to input signal to a linear time invariant system, h of n tends to impulse response, y1 of n tends to output of the system. y1 of n becomes input to a second linear time invariant system with impulse response h2 of n. The output is y of n equal to y1 of n star h2 of n equal to x of n star h1 of n star h2 of n. The right hand side of equation 1 indicates the input x of n is applied to an equivalent system having an impulse response, say h of n, which is equal to the convolution of the two impulse responses, that is h of n equal to h1 of n star h2 of n and y of n equal to x of n star h of n. Implications of the associative A and the associative and commutative B properties of convolution. Distributive law. X of n star h1 of n plus h2 of n equal to x of n star h1 of n plus x of n star h2 of n. If we have two linear time invariant systems with impulse responses h1 of n and h2 of n excited by the same input signal n, the sum of the two responses is identical to the response of an overall system with impulse response. H of n equal to h1 of n plus h2 of n. Thus, overall system is viewed as a parallel combination of the two linear time invariant systems. Interpretation of the distributive property of convolution. Two LTI systems connected in parallel can be replaced by a single system with h of n equal to h1 of n plus h2 of n. Casual linear time invariant systems. A casual system is one whose output at time n depends only on the present and past inputs but does not depend on future inputs. In other words, the output of the system at time instant n, say n equal to n naught, depends only on values of x of n for n less than or equal to n naught. In case of a LTI system, causality can be translated to a condition on the impulse response. Consider a LTI system having an output at time n equal to n naught given by the convolution formula. Y of n naught equal to summation k equal to minus infinity to plus infinity h of k into x of n naught minus k. Let us divide the sum into two sets of terms, one having present and past values of input, that is x of n less than or equal to n naught, and other having set involving future values of input, that is x of n greater than n naught. Thus we obtain y of n naught equal to summation k equal to 0 to infinity h of k into x of n naught minus k plus summation k equal to infinity to minus 1 h of k into x of n naught minus k equal to h of 0 into x of n naught plus h of 1 into x of n naught minus 1 plus h of 2 into x of n naught minus 2 plus etc. plus h of minus 1 into x of n naught plus 1 plus h of minus 2 into x of n naught plus 2 plus etc. The terms in first sum involve x of n naught, x of n naught minus 1, which are the present and past values of the input signal. The terms in second sum involve input signal component x of n naught plus 1, x of n naught plus 2. If the output at time n equal to n naught is to depend only on past and present inputs, then impulse response of the system must satisfy the condition h of n equal to 0 when n less than 0. An LTI system is causal if and only if its impulse response is 0 for negative values of n. A sequence that is 0 for n less than 0 is called a causal sequence, and a sequence that is non-zero for n less than 0 and n greater than 0 is called a non-causal sequence. If the input to a causal LTI system is a causal sequence, that is, if x of n equal to 0 for n less than 0, the limit on the convolution formula is further restricted. Y of n equal to summation k equal to 0 to n h of into x of n minus k equal to summation k equal to 0 to n x of k into h of n minus k. Example: determine the unit step response of the LTI system with impulse response h of n equal to a power n into u of n modulus of a less than 1. Solution: since the input signal is a unit step which is a causal signal and the system is also causal, we can use special form of the convolution formula. Y of n equal to summation k equal to 0 to n a power k equal to 1 minus a power n plus 1 divided by 1 minus a. Stability of linear time invariant systems. An arbitrary relaxed system is BABO stable if and only if its output sequence y of n is bounded for every bounded input x of n. If x of n is bounded, there exists a constant mx such that modulus of x of n less than or equal to mx less than infinity. Similarly, if the output is bounded, there exists a constant my such that modulus of y of n less than my less than infinity for all n. Convolution formula y of n equal to summation k equal to minus infinity to plus infinity h of k into x of n minus k. Take absolute value in both sides. Modulus of y of n equal to modulus of summation k equal to minus infinity to plus infinity h of k into x of n minus k. Absolute value of sum of terms is always less than or equal to the sum of absolute values of the terms. Hence, modulus of y of n less than or equal to summation k equal to minus infinity to plus infinity modulus of h of k into modulus of x of n minus k. If the input is bounded, there exists a finite number mx such that modulus of x of n less than or equal to mx. Substitute upper bound for x of n in above equation. Modulus of y of n less than or equal to mx summation k equal to minus infinity to plus infinity modulus of h of k. The output is bounded if the impulse response of the system satisfies the condition sh equal to summation k equal to minus infinity to plus infinity modulus of h of k less than infinity. A LTI system is stable if its impulse response is absolutely summable. If sh equal to infinity, there is a bounded input for which the output is not bounded. X of n equal to h star of minus n divided by modulus of h star of minus n when h of n not equal to 0 and 0 when h of n equal to 0. Here h star of n is the complex conjugate of h of n for n equal to 0. Y of 0 equal to summation k equal to minus infinity to plus infinity x of minus k into h of k equal to summation k equal to minus infinity to plus infinity modulus of h of k the whole square divided by modulus of h of k equal to sh. Thus, if sh equal to infinity, a bounded input produces an unbounded output since y of 0 equal to infinity. Example, determine the range of values of the parameter a for which the LTI system with below impulse response is stable. H of n equal to a star u of n. Solution, the system is casual. Consequently, the lower index on the summation begins with k equal to 0. Hence, summation k equal to 0 to infinity modulus of a power k equal to summation k equal to 0 to infinity modulus of a whole power k equal to 1 plus modulus of a power 1 plus modulus of a the whole square plus etc. Clearly, this geometric series converges to summation k equal to 0 to infinity modulus of a whole power k equal to 1 by 1 minus modulus of a, provided modulus of a less than 1. Therefore, the system is stable if modulus of a less than 1. Otherwise, it is unstable. In effect, h of n must decay exponentially toward 0 as n approaches infinity for the system to be stable. Example, determine the range of values of a and b for which LTI system with below impulse response is stable. H of n equal to a power n for n greater than or equal to 0, then b power n for n less than 0. Solution, the system is non-casual. The condition on stability yields summation n equal to minus infinity to plus infinity modulus of h of n equal to summation n equal to 0 to infinity modulus of a power n plus summation n equal to minus infinity to minus 1 modulus of b power n. From previous example, we have determined the first sum converges to modulus of a less than 1. Second sum can be manipulated as below. Summation n equal to minus infinity to minus 1 modulus of b power n equal to summation n equal to 1 to infinity 1 by modulus of b power n equal to 1 by modulus of b into within the bracket 1 plus 1 by modulus of b plus 1 by modulus of b square plus etc. equal to beta into 1 plus beta square plus etc. equal to beta divided by 1 minus beta, where beta equal to 1 divided by modulus of b must be less than unity for the geometric series to converge. Consequently, the system is stable if both modulus of a less than 1 and modulus of b greater than 1 are satisfied. Systems with finite duration and infinite duration impulse response. The class of LTI systems is subdivided into two types: finite duration impulse response FIR, infinite duration impulse response IIR. Finite duration impulse response FIR. An FIR system has an impulse response that is 0 outside of some finite time interval h of n equal to 0 for n less than 0 and n greater than or equal to m. The convolution formula for which a system reduces to y of n equal to summation k equal to 0 to m minus 1 h of k into x of n minus k. Infinite duration impulse response IIR. An IIR linear time invariant system has an infinite duration impulse response. Its output based on the convolution formula is y of n equal to summation k equal to 0 to infinity h of k into x of n minus k. Correlation of discrete time systems. A mathematical operation that closely resembles convolution is correlation. Like in convolution, two signals sequences are involved in correlation. In contrast to convolution, computing the correlation between two signals is to measure the degree to which the two signals are similar and thus to extract some information that depends to a large extent on the application. Correlation of signals is often encountered in radar, sonar, digital communications, geology, and other areas in science and engineering. Let us suppose we have two signal sequences x of n and y of n. In radar and active sonar applications, x of n represents the sampled version of the transmitted signal. Y of n represents the sampled version of the received signal at the output of the analog to digital A/D. Received signal sequence y of n is represented as y of n equal to a into x of n minus capital D plus w of n. A is some attenuation factor representing the signal loss involved in the round trip transmission of the signal x of n. T is the round trip delay, assumed to be an integer multiple of the sampling interval. W of n represents the additive noise that is picked up by the antenna and any noise generated by the electronic components and amplifiers in the front end of the receiver. In digital communications, the information to be transmitted from one point to another is usually converted to binary form, that is, sequence of zeros and ones which are then transmitted to intended receivers. To transmit a 0, we can transmit signal sequence x0 of n for 0 less than or equal to n less than or equal to l minus 1, and to transmit a1, we can transmit signal sequence x1 of n for 0 less than or equal to n less than or equal to l minus 1, where l is an integer that denotes the number of samples in each of the two sequences. Often, x1 of n is selected to be negative of x0 of n. The signal received is represented as y of n equal to xi of m and w of n, where I equal to 0, 1, then 0 less than or equal to n less than or equal to l minus 1. W of n represents the additive noise. The uncertainty is whether x0 of n or x1 of n is the signal component in y of n. The receiver knows the possible transmitted sequences and is faced with the task of comparing the received signal with both x0 of n and x1 of n to determine which of the two signals better matches y of n. This comparison process is performed by means of the correlation operation. Cross correlation and autocorrelation sequences. The cross correlation of x of n and y of n is a sequence Rxy of L, which is defined as Rxy of L equal to summation n equal to minus infinity to plus infinity x of n into y of n minus L, where L equal to 0, plus or minus 1, plus or minus 2, etc. Or equivalently as Rxy of L equal to summation n equal to minus infinity to plus infinity x of n minus L into y of n, where L equal to 0, plus or minus 1, plus or minus 2, etc. Index I is the time, shift or lag parameter. Subscript xy indicate the sequences being correlated. If we reverse the roles of x of n and y of n, Rxy of L equal to summation n equal to minus infinity to plus infinity y of n into x of n minus L, or equivalently as Ryx of L equal to summation n equal to minus infinity to plus infinity y of n plus L into x of n. Therefore, Ryx of L is the folded version of Rxy of L, where folding is done with respect to L equal to 0. Hence, Ryx of L provides exactly the same information as Rxy of L with respect to the similarity of x of n to y of n. The computation of the cross correlation sequence involves shifting one of the sequence, multiplication of two sequences, summing over all values of product sequence. The autocorrelation of x of n, where y of n equal to x of n, is defined as Rxy of L equal to summation n equal to minus infinity to plus infinity x of n into x of n minus L, or equivalently as Rxy of L equal to summation n equal to minus infinity to plus infinity x of n minus L into x of n. If x of n and y of n are casual sequences of length capital N, that is x of n equal to y of n equal to 0 for n less than 0 and n greater than or equal to capital N. The cross correlation and autocorrelation sequences are Rxy of L equal to summation n equal to I2 capital N minus modulus of k minus 1 x of n into y of n minus L, and Rx x of L equal to summation n equal to capital N minus modulus of k minus 1 x of n into x of n minus L, where I equal to 1, k equal to 0 for 1 greater than or equal to 0 and I equal to 0, k equal to 1 for 1 less than or equal to 0. Properties of the autocorrelation and cross correlation sequences. The autocorrelation and cross correlation sequences have a number of properties. Autocorrelation sequence of a signal attains its maximum value at 0 lag if any or both the signals involved in the cross correlation scaled. The shape of the cross correlation sequence does not change, only the amplitudes of the sequences are scaled accordingly. Since scaling is unimportant, it is often desirable to normalize the autocorrelation and cross correlation sequences to the range from -1 to +1. In case of autocorrelation sequence, we can simply divide by Rxy of 0. Normalized autocorrelation sequences rho xx of L equal to Rxx of L divided by Rxx of 0. Normalized cross correlation sequences rho xx of L equal to Rxx of L divided by square root of Rxx of 0 into Ryy of 0. Example: compute the autocorrelation of the signal. X of n equal to a power n into u of n, where 0 less than a less than 1. Solution: since x of n is an infinite duration signal, its autocorrelation also has infinite duration. If L greater than or equal to 0, or xx of L equal to summation n equal to 1 to infinity, x of n into x of n minus 1 equal to summation n equal to 1 to infinity, a power n into a power n minus 1. On further simplification, Rxx of L equal to a power minus 1 into summation n equal to 1 to infinity, a square whole power n. Since a less than 1, the infinite series converges and we obtain Rxx of L equal to 1 divided by 1 minus a square into a power minus 1 for L greater than or equal to 0. For L less than 0, we have Rxx of L equal to summation n equal to 0 to infinity x of n into x of n minus 1 equal to a power minus 1 into summation n equal to 0 to infinity a square whole power n equal to 1 divided by 1 minus a square into a power minus 1, where L less than 0. But when L is negative, a power minus 1 equal to a power 0. Thus, the two relations for Rxy of L can be combined into FOL. Rxx of L equal to 1 divided by 1 minus a square into a power minus 1, where minus infinity less than L less than infinity. The sequence Rxx of L is Rxx of minus L equal to Rxx of L and Rxx of 0 equal to 1 divided by 1 minus a square. Therefore, the normalized autocorrelation sequences rho xx of L equal to Rxx of L divided by Rxx of 0 equal to a power minus 1, where minus infinity less than L less than infinity. Correlation of periodic sequences. In this section, we consider the cross correlation sequences of power signals and in particular periodic signals. Let x of n and y of n be two power signals. The cross correlation sequence is defined as Rxx of L equal to limit capital M tends to infinity 1 divided by 2 capital M plus 1 into summation n equal to minus m to capital M x of n into y of n minus L. If x of n equal to y of n, the autocorrelation sequence of a power signal is defined as Rxx of L equal to limit capital M tends to infinity 1 divided by 2m plus 1 into summation n equal to minus capital M to plus m x of n into x of n minus L. Figure: computation of the autocorrelation of the signal x of n equal to a power n, where 0 less than a less than 1. Computation of correlation sequences. The procedure for computing the cross correlation sequence between x of n and y of n involves shifting one of the sequence, say x of n, to obtain x of n minus 1. multiplying the shifted sequence by y of n to obtain the product sequence y of n into x of n minus 1, and then summing all the values of the product sequence to obtain Ryx of L. The procedure for computing the convolution is directly applicable to computing the correlation of two sequences. If we fold y of n to obtain y of minus n, then the convolution of x of n with y of minus n is identical to the cross correlation of x of n with y of n. That is, Rx of L equal to x of n star y of minus n, where n equal to L. Input-output correlation sequences. In this section, we derive two input-output relationships for LTI systems in the correlation domain. Input-output relation for cross-correlation, input-output relation for cross-correlation Rxy of n. Let us assume that a signal x of n with known autocorrelation Rx of L is applied to an LTI system with impulse response h of n producing the output signal. Y of n equal to h of n star x of n equal to summation k equal to minus infinity to plus infinity h of k into x of n minus k. The cross correlation between the output and the input signal is Ryx of L equal to y of L star x of minus L equal to h of L star x of L star x of minus L, or Yx of L equal to h of L star or xx of L. The autocorrelation of the output signal can be obtained by x of n equal to y of n and the properties of convolution, or Yx of L equal to y of L star y of minus L. After simplification, it becomes h of L star x of L star h of minus L star x of minus L. Then h of L star h of minus L star x of L star x of minus L equal to or h of L star or xx of L. By evaluating L equal to 0 or Yx of 0 equal to summation k equal to minus infinity to plus infinity or h of k into or xx of k. Flowchart for software implementation of cross correlation is given as followed. Discrete time signals. Digital signals are discrete in both time, the independent variable, and amplitude, the dependent variable. Signals that are discrete in time but continuous in amplitude are referred to as discrete time signals. Discrete time signals are data sequences. A sequence of data is denoted x of n or simply x of n when the meaning is clear. The elements of the sequence are called samples. The index n associated with each sample is an integer. If appropriate, the range of n will be specified. Quite often, we are interested in identifying the sample where n equal to 0. This is done by putting an arrow under that sample. For instance, x of n equal to 0.35, 1, 1.5, minus 0.6, minus 2, etc. The arrow is often omitted if it is clear from the context which sample is x of 0. Sample values can either be real or complex. Graphical representation of discrete time signal is given as followed, where x of n falls on y-axis and n falls on x-axis. Besides the graphical representation of a discrete time signal or sequence as illustrated in above figure, there are some alternative representations that are often more convenient to use. These are: number 1. Functional representation. X of n equal to 1 for n equal to 1, 3. 4 for n equal to 2, then 0 elsewhere. Number 2. Tabular representation. According to the functional criteria, n and x of n are replaced and are represented as followed. Now we can see the n values -2, -1, 0, 1, 2, 3, 4, 5, etc. Then x of n 0, 0, 0, 1, 4, 1, 0, 0, etc. Number 3. Sequential representation. The sequential representation is decoded from the tabular representation and is given below. X of n equal to 0, 0, 1, 4, 1, 0, 0, etc. Some elementary discrete time signals. In our study of discrete time signal and systems, there are a number of basic signals that appear often and play an important role. They are described here. Unit sample signal. The unit sample sequence is defined as delta of n equal to 1 for n equal to 0, 0 for n not equal to 0. Unit sample sequence is a signal that is 0 everywhere except at n equal to 0, where its value in unity. The signal is sometimes referred as unit impulse. The graphical representation of the unit sample signal comes as followed, in which y-axis is taken as delta of n and x-axis is taken as n. Unit step signal. The unit step signal is denoted as u of n and defined as u of n equivalents 1 for n greater than or equal to 0, 0 for n less than 0. The unit step sequence is one that has an amplitude of 0 for negative indices and an amplitude of 1 for non-negative indices. The graphical representation of unit step signal is given below. The y-axis is taken as u of n and x-axis is taken as n. Unit ramp signal. The unit ramp signal is denoted as ur of n and is defined as ur of n is equivalent to n for n greater than or equal to 0 and 0 for n less than 0. Graphical representation of the unit ramp signal is as followed. The ur of n is taken as the y-axis and the x-axis is denoted by n. Exponential signal. The exponential signal is of the form x of n equal to a power n for all n. If the parameter a is real, then x of n is a real signal. When the parameter a is a complex value, it can be expressed as a equivalents to r into e power j theta, where r and theta are now the parameters. Hence, we can express x of n as x of n equal to r power n e power j theta n, which is equal to r power n into cos theta n plus j sin theta n. The graphical representation of exponential signals is given below, where x of n falls on x-axis and n falls on y-axis. Classification of discrete time signals. Energy and power signals. The energy E of a signal x of n is defined as E equivalents to summation n equal to minus infinity to plus infinity modulus of x of n the whole square. The energy of a signal can be finite or infinite. If E is finite, then x of n is called an energy signal. Subscript x is added to E to emphasize that Ex is the energy of signal x of n. Many signals that possess infinite energy have a finite average power. The average power of a discrete time signal x of n is defined as P equal to limit n tends to infinity 1 divided by 2 into capital N plus 1 into summation n equal to minus capital N to plus capital N modulus of x of n the whole square. If we define the signal energy of x of n over the finite interval minus capital N less than or equal to n less than or equal to plus capital N as E capital N is equivalent to summation n equal to minus capital N to plus capital N modulus of x of n the whole square. Then signal energy is E is equivalent to limit n tends to infinity En. and the average power of the signal x of n is p is equivalent to limit n tends to infinity 1 divided by 2n plus 1 into en. If e is finite, p equal to 0. If e is infinite, average power p may be finite or infinite. If p is finite and non-zero, the signal is called a power signal. Periodic signals and aperiodic signals. A signal x of n is periodic with period capital N greater than 0 if and only if x of n equal to x of n plus capital N for all n. The smallest value of capital N for above equation is satisfied is called the period. If there is no value of capital N satisfies x of n equal to x of n plus capital N, the signal is called non-periodic or aperiodic sinusoidal signal of the form x of n equal to a into sine 2 pi f naught into n is periodic when f naught is a rational number, that is, if f naught can be expressed as f naught is equal to k divided by capital N, where k and n are integers. If x of n is a periodic signal with the fundamental period capital N and it takes on finite values, its power is given by p equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 modulus of x of n the whole square. Consequently, periodic signals are power signals. Symmetric even and antisymmetric odd signals. A real valued signal x of n is called symmetric even if x of minus n equal to x of n. On the other hand, a signal x of n is called antisymmetric odd if x of minus n equal to minus x of n. Even signal, odd signal. Graphical representation of even and odd signal is given as followed. When x of n falls on y-axis and n falls on x-axis, the even signal component is formed by adding x of n to x of minus n and dividing by 2, that is, xe of n equal to 1 by 2 into x of n plus x of minus n. The odd signal component x naught of n is x naught of n equal to 1 by 2 into x of n minus x of minus n. An arbitrary signal can be expressed as x of n equal to xe of n plus x naught of n. Simple manipulations on discrete time signal. Transformation of the independent variable time. Shifting. A signal x of n may be shifted in time by replacing the independent variable n by n minus k, where k is an integer. If k is a positive integer, the time shift resulting in a delay of the signal k units of time. If k is a negative integer, the time shift results in an advance of the signal by modulus of k units in time. Graphical representation of a signal, its delay and its advanced version are given as followed. In figure A, x of n falls in the y-axis and the n falls in the x-axis. In figure B, y-axis is represented by x of n minus 3 and x-axis represents n. In figure C, x of n plus 2 falls on y-axis and n falls on x-axis. Folding. Another modification of the time base is to replace the independent variable n by minus n. The result of this operating is called folding or reflection of the signal about the time origin n equal to 0. Graphical representation of folding and shifting operations is illustrated as followed in figure A. Y-axis is denoted by x of n and the x-axis is denoted as n. In figure B, y-axis is denoted as x of minus n and x-axis as n. In figure C, the y-axis is represented as x of minus n plus 2. Downsampling. Downsampling is a more specific term which refers to the process of throwing away samples without the low-pass filtering operation. The following are the graphical representation of the downsampling, where the y-axis of the figure A and B are x of n and x of 2n respectively, and the x-axis is given by n. A basic downsampling operation is as follows. The downsampler is 2 here, therefore 2 is down sampled to 1 and minus 2 is downsampled to minus 1. A downsampling operation can be viewed as the combination of two steps as follows. It first kills some samples as explained below. In this, the odd samples are killed as shown in the example. Then it compresses the resultant as shown below. When it gets compressed, minus 2 becomes minus 1, minus 4 becomes minus 2, 2 becomes 1 and 4 becomes 2. Addition, multiplication and scaling of sequences. Amplitude scaling of a signal by a constant capital A is accomplished by multiplying the value if every signal sample of capital A. Consequently, we obtain y of n equal to capital AX of n minus infinity less than n less than infinity. The sum of two signals x1 of n and x2 of n is a signal y of n whose value at any instant is equal to the sum of the values of these signals at that instant. Y of n is equal to x1 of n plus x2 of n minus infinity less than n less than infinity. The product of two signals is similarly defined on a sample-to-sample basis as y of n equal to x1 of n into x2 of n minus infinity less than n less than infinity. Discrete time systems described by differential equations. FIR systems are implemented directly by the convolution summation as the realization involves addition, multiplication and a finite number of memory locations. However, IIR systems implementation by convolution is clearly impulse since it requires a infinite number of memory locations, multiplications and additions. But IIR system can be realized in forms other than those suggested by the convolution summation. Within the general class of IIR systems, this family of discrete time systems is described by difference equations. Subclass of IIR systems is useful in a variety of practical applications including implementation of digital filters and the modeling of physical phenomena and physical systems. Recursive and non-recursive discrete time systems. Recursive system. A system whose output y of n at time n depends on any number of past output values y of n minus 1, y of n minus 2, etc. is called a recursive system. Figure realization of a recursive cumulative averaging system. There are many systems where it is either necessary to express the output of the system not only in terms of the present and past values of the input but also in terms of the past output values. To compute the cumulative average of a signal x of n in the interval 0 less than or equal to k less than or equal to n defined as y of n equal to 1 divided by n plus 1 into summation k equal to 0 to n x of k where n equal to 0, 1, etc. Y of n can be computed by utilizing the previous output value y of n minus 1. N plus 1 into y of n equal to summation k equal to 0 to n minus 1 x of k plus x of n equal to n into y of n minus 1 plus x of n, and hence y of n equal to n divided by n plus 1 into y of n minus 1 plus 1 divided by n plus 1 into x of n. Recursive system to compute the square root of a number. Square root algorithm. The square root of a positive number a is computed by using the iterative algorithm. Xn equal to 1 by 2 into Sn minus 1 plus a divided by Sn minus 1 where n equal to 0, 1, etc. Now consider the recursive system. Y of n equal to 1 by 2 into y of n minus 1 plus x of n divided by y of n minus 1. In general, we can formulate more complex casual recursive systems in which the output y of n is a function of several past output values and present and past inputs. Y of n equal to f of y of n minus 1, comma, y of n minus 2, comma, etc. y of n minus capital N, comma, x of n, comma, x of n minus 1, comma, etc. x of n minus capital M. Non-recursive systems. A system whose output y of n at time n depends only on the present and past inputs is called a non-recursive systems. Y of n equal to f of x of n, comma, x of n minus 1, comma, etc. x of n minus capital M. Basic form for a casual and realizable are shown here. A represents non-recursive and B represents recursive system. The output of a recursive system should computed in order, that is y of 0, comma, y of 1, comma, y of 2, etc. Whereas for a non-recursive system, the output can be computed in any order, that is y of 200, comma, y of 3, comma, y of 300, etc. Linear time invariant systems characterized by constant coefficient difference equations. Earlier we treated LTA systems and characterized them in terms of their impulse responses. In this section, we focus on a family of LTA systems described by an input-output relation called a difference equation with constant coefficients. Systems described by constant coefficient linear difference equations are a subclass of the recursive and non-recursive systems. Block diagram realization of a simple recursive system. Y of n equal to a into y of n minus 1 plus x of n. We compute successive values of y of n for n greater than or equal to 0, beginning with y of 0. Y of 0 equal to a into y of minus 1 plus x of 0. Y of 1 equal to a into y of 0 plus x of 1 equal to a square into y of minus 1 plus a into x of 0 plus x of 1. Y of 2 equal to a into y of 1 plus x of 2 equal to a cube into y of minus 1 plus a square into x of 0 plus a into x of 1 plus x of 2. Y of n equal to a into y of n minus 1 plus x of n equal to a power n plus 1 into y of minus 1 plus a power n into x of 0 plus a power n minus 1 into x of 1 plus etc. plus a into x of n minus 1 plus x of n. Y of n equal to a power n plus 1 into y of minus 1 plus summation k equal to 0 to n a power k into x of n minus k for n greater than or equal to 0. The zero input response is a characteristic of the system itself. It is known as the natural or free response of the system. The zero state response depends on the nature of the system and the input signal, since the output is forced upon it by the input signal. It is called the forced response of the system. The zero state response or forced response of the system is given by y zs of n equal to a power n plus 1 into y of minus 1 plus summation k equal to 0 to n a power k into x of n minus k for n greater than or equal to 0. If the system is initially non-relaxed, that is y of minus 1 not equal to 0 and the input x of n equal to 0 for all n, the output of the system ith zero input is called zero input response or natural response and is denoted by yzs of n. If x of n equal to 0 for minus infinity less than n less than infinity, yzi of n equal to a power n plus 1 into y of minus 1 for n greater than or equal to 0. The total response of the system can be expressed as y of n equal to yzi of n plus yzs of n. Y of n equal to minus summation k equal to 1 to capital N ak into y of n minus k plus summation k equal to 0 to capital M bk into x of n minus k, or summation k equal to 1 to capital N ak into y of n minus k equivalents to summation k equal to 0 to capital M bk into x of n minus k for a naught equivalents to 1. A system is linear if it satisfies the following three requirements. Number 1. The total response is equal to the sum of the zero input and zero state responses, that is, y of n equal to yzi of n plus yzs of n. Number 2. The principal superposition applies to the zero state response within the bracket zero state linear. Number 3. The principle of superposition applies to the zero input response within the bracket zero input linear. If a system does not satisfy all three separate requirements, it is nonlinear. The recursive system described by a linear constant coefficient difference equation is linear and time invariant. Example: if recursive system defined by difference equation is linear, y of n equal to a into y of n minus 1 plus x of n. Solution: from above expressions we determine y of n equal to yzi of n plus yzs of n. Thus, first requirement for linearity is satisfied. To check for second requirement, let us assume x of n equal to c1 into x1 of n plus c2 into x2 of n. Yzs of n equal to summation k equal to 0 to n a power k into c1 into x1 of n minus k plus c2 into x2 of n minus k, which when simplified becomes equal to c1 into summation k equal to 0 to n a power k into x1 of n minus k plus c2 into summation k equal to 0 to n a power k into x2 of n minus k is further simplified as equal to c1 into yzs 1 of n plus c2 into yzs 2 of n. Hence, yzs of n satisfies the principle of superposition and thus the system is zero state linear. Now assume that y of minus 1 equal to c1 into y1 of minus 1 plus c2 into y2 of minus 1. Yzi of n equal to a power n minus 1 into c1 into y1 of minus 1 plus c2 into y2 of minus 1 is simplified as equal to c1 into a power n minus 1 into y1 of minus 1 plus c2 into a power n plus 1 into y2 of minus 1 is further simplified as c1 into yzi 1 of n plus c2 into yzi 2 of n. Hence the system is zero input linear. Since the system satisfies all three conditions for linearity, it is linear. Solution of linear constant coefficient difference equations. Given a linear constant coefficient difference equation as the input-output relationship describing a LTI system, our objective is to determine an explicit expression for the output y of n. The method that is developed is termed the direct method. The Z transform approach is called the indirect method. Basically, the goal is to determine the output y of n greater than or equal to 0, the system given a specific input x of n greater than or equal to 0, and a set of initial conditions. The direct solution method assumes that the solution is the sum of two parts, y of n equal to yh of n plus yp of n. YH of n is known as the homogeneous or complementary solution. YP of n is called the particular solution. The homogeneous solution of a difference equation. Let us assume input x of n equal to 0. We will first obtain the solution to the homogeneous difference equation. Summation k equal to 0 to capital N, ak into y of n minus k equal to 0. The procedure for solving a linear constant coefficient difference equation directly is very similar to the procedure for solving a linear constant coefficient differential equation. We assume that the solution is in the form of an exponential, that is y of n equal to lambda power n, where subscript h on y of n is used to denote the solution to the homogeneous difference equation. The particular solution of the difference equation. The particular solution yp of n is required to satisfy below difference equation for the specific input signal x of n for n greater than or equal to 0. Summation k equal to 1 to capital N, ak of y of n minus k equivalents to summation k equal to 0 to capital M, bk into x of n minus k. In other words, yp of n is any solution satisfying summation k equal to 0 to capital N, ak into yp of n minus k equal to summation k equal to 0 to capital M, bk into x of n minus k for a equivalents to 1. Example, determine the particular solution of the first order difference equation y of n plus a1 into y of n minus 1 equal to x of n for modulus of a1 less than 1, when the input x of n is a unit step sequence, that is x of n equal to u of n. Solution. Since the input sequence x of n is a constant for n greater than or equal to 0, the form of solution is also constant. Hence, the assumed solution of difference equation to the forcing function x of n, called the particular solution of the difference equation, is yp of n equal to k into u of n, where k is a scale factor, k into u of n plus a1 into k into u of n minus 1 equal to u of n. To determine k, we must evaluate this equation for any n greater than or equal to 1. K plus a1 into k equal to 1, k equal to 1 divided by 1 plus a1. Therefore, the particular solution to the difference equation is yp of n equal to 1 divided by 1 plus a1 into u of n. The total solution of the difference equation. The linearity property of the linear constant coefficient difference equation allows us to add the homogeneous solution and the particular solution in order to obtain the total solution. Thus, y of n equal to yh of n plus yp of n. The resulting sum y of n contains the constant parameters modulus of ci embodied in the homogeneous solution component yh of n. These constants can be determined to satisfy the initial conditions. When the system response of a component does not go to 0, as n approached infinity, it is called the steady state response of the system. This response persists as long as the input persists. When the response of the component dies out as n approaches infinity, it is called the transient response of the system. Example, determine the total solution y of n greater than or equal to 0 to the difference equation y of n plus a1 into y of n minus 1 equal to x of n. When x of n is a unit step sequence, that is x of n equal to u of n and y of minus 1 is the initial condition. Solution. The homogeneous solution is yk of n equal to c of minus a1 whole power n, and the particular solution is yp of n equal to 1 divided by 1 plus a1. Consequently, the total solution is y of n equal to c of minus a1 power n plus 1 divided by 1 plus a1 for n greater than or equal to 0 is called equation number 2, where the constant c is determined to satisfy the initial condition y of minus 1. To obtain the zero state response of the system described in equation 1, we set y of minus 1 equal to 0. Evaluate c at n equal to 0, y of 0 plus a1 into y of minus 1 equal to 1, y of 0 equal to 1. On the other hand, equation 2 evaluated at n equal to 0 yields y of 0 equal to c plus 1 divided by 1 plus a1, c plus 1 divided by 1 plus a1. Substitute c in equation number 2 yields the zero state response of the system. Yzs of n equal to 1 minus a1 power n minus 1 divided by 1 plus a1 for n greater than or equal to 0. If we evaluate the parameter c in equation number 2 under the condition y of minus 1 not equal to 0, then total solution will include the zero input response as well as the zero state response of the system. In this equation 1 yields y of 0 plus a1 into y of minus 1 equal to 1, y of 0 equal to minus a1 into y of minus 1 plus 1. On the other hand, equation 2 yields y of 0 equal to c plus 1 divided by 1 plus a1. By equating these two relations, we obtain c plus 1 divided by 1 plus a1 equal to minus a1 into y of minus 1 plus 1, c equal to minus a1 into y of minus 1 plus a1 divided by 1 plus a1. Finally, if we substitute this value of c into equation 2, we obtain y of n equal to minus a1 power n plus 1 into y of minus 1 plus 1 minus a1 power n minus 1 divided by 1 plus a1 for n greater than or equal to 0, which when simplified gives yzi of n plus yzs of n. The impulse response of a linear time invariant recursive system. The impulse response of a linear time invariant system was previously defined as the response of the system to unit sample excitation, that is x of n equal to infinity of n. In the case of a recursive system, h of n is simply equal to the zero state response of the system when the input x of n equal to infinity of n and the system is initially relaxed. The zero state responses yzs of n equal to summation k equal to 0 to n a power k into x of n minus k. With x of n equal to infinity of n is substituted in above equation. Yzs of n equal to summation k equal to 0 to n a power k into infinity of n minus k equal to a power n for n greater than or equal to 0. Hence, the impulse response of the first order recursive system described as h of n equal to a power n into u of n. In general case of an arbitrary LTI recursive system, the zero state response expressed in terms of the convolution summation is yzs of n equal to summation k equal to 0 to n h of k into x of n minus k for n greater than or equal to 0. When the input is impulse, that is x of n equal to infinity of n, yzs of n equal to h of n. Discrete time systems. A device or an algorithm that performs some prescribed operation on a discrete time signal is called a discrete time system. A discrete time system is a device or algorithm that operates on a discrete time signal called the input or excitation according to some well-defined rule to produce another discrete time signal called the output or response of the system. Discrete time system is represented as y of n equal to t of x of n, where x of n is the input signal, y of n is the output, t denotes the processing performed by the system on x of n to produce y of n. From the figure, we can clearly see input signal and output signal. Block diagram representation of a discrete time system. Input-output description of systems. The general input-output relationship x of n tends to y of n. Y of n is the response to the system t to the excitation x of n. Classification of discrete time systems. Discrete time systems, like continuous time systems, can be classified in a variety of ways. The property must hold for every input signal to the system. Static versus dynamic systems. A discrete time system is called static or memoryless if its output at any instant n depends at most on the input sample at the same time, but not on past or future samples of the input. A discrete time system is called a dynamic or to have memory if the output of the system at time n is completely determined by the input samples in the interval from n minus capital N to n inside the bracket capital N greater than or equal to 0. The system is said to have memory of duration capital N. If 0 less than capital N less than infinity, the system is said to have finite memory, whereas if capital N equal to infinity, the system is said to have infinite memory. The system described by the following input-output equations are both static or memoryless. Y of n equal to ax of n, y of n equal to nx of n plus bx cube of n. The system described by the following input-output equations are both dynamic systems or systems with memory. Y of n equal to x of n plus 3x of n minus 1. Y of n is equal to summation k equal to 0 to n x of n minus k. Y of n equal to summation k equal to 0 to infinity x of n minus k. Time invariant versus time variant systems. We can subdivide the general class of systems into two broad categories: time invariant systems and time variant systems. A system is called time invariant if its input-output characteristics do not change with time. Y of n equal to t of x of n. A relaxed system t is time invariant or shift invariant if and only if y of n is the response to the system t to the excitation x of n. Implies that y of n minus k is the response to the system t to the excitation x of n minus k. For every input signal x of n and every shift k, if the output y of n comma k not equal to y of n minus k, even for one value of k, the system is time variant. Adder. It is not necessary to store either one of the sequences in order to perform addition. The addition operation is memoryless. Y of n equal to x1 of n plus x2 of n. Graphical representation of an adder. A constant multiplier. This operation is memoryless. X of n when multiplied by a given y of n, and it can also be termed as y of n is equal to a into x of n. Graphical representation of a constant multiplier. A signal multiplier. Multiplication operation is also memoryless. x1 of n when multiplied by x2 of n gives y of n, and it can also be termed as y of n is equal to x1 of n into x2 of n. A unit delay element. A unit delay is a special system that simply delays the signal passing through it by one sample. This building block requires memory. Y of n equal to x of n minus 1. When z inverse is applied to x of n, then y of n becomes x of n minus 1. A unit advance element. A unit advance moves the input x of n ahead of one sample in time to yield x of n plus 1. When z is applied to x of n, then y of n becomes x of n plus 1. Examples of a time invariant A and some time variant systems B to D. Differentiator is a time invariant system, whereas the time multiplier, folder and modulator are time invariant. Examples of a time invariant A and some time variant systems B to D. Linear versus nonlinear systems. The general class of systems can be subdivided into linear systems and nonlinear systems. A linear system is one that satisfies the superposition principle. The principle of superposition requires that the response of the system to a weighted sum of signals to equal to the corresponding weighted sum of the responses output of the system to each of the individual input signals. A relaxed T system is linear if and only if A1 x1 of n plus A2 x2 of n equal to A1t of x1 of n plus A2t of x2 of n for any arbitrary input sequences x1 of n and x2 of n and any arbitrary constants A1 and A2. Graphical representation of the superposition principle is given as followed. Graphical representation of the superposition principle. If a relaxed system does not satisfy the superposition principle as given by definition, it is called nonlinear. Causal versus non-causal systems. A system is said to be causal if the output of the system at any time n depends only on present and past inputs but does not depend on the future inputs. A system is said to be non-causal if the system has an output that depends not only on present and past inputs but also future inputs. Stable versus unstable systems. Stability is an important property considered in practical application of a system. Unstable systems usually exhibit erratic and extreme behavior and cause overflow in any practical implementation. Definition. An arbitrary relaxed system is said to be bounded input, bounded output, BIBO. Stable if and only if every bounded input produces a bounded output. A system is BIBO unstable if a bounded input sequence produces an unbounded output. Interconnection of discrete time systems. There are two basic ways in which system can be interconnected: in cascade series or in parallel. Cascade A and parallel B interconnections of system. Implementation of discrete time systems. System design and implementation are usually treated jointly rather than separately. System design ID driven by the method of implementation and by implementation constraints such as cost, hardware limitations, size limitations and power requirements. Structures for the realization of linear time invariant systems. The realization using separate delays memory for both the input and output signal samples is called a direct form 1 structure. Y of n equal to minus a1 into y of n minus 1 plus b naught into x of n plus b1 into x of n minus 1 is called equation number 1. The first is a non-recursive system described by equation v of n equal to b naught into x of n plus b1 into x of n minus 1. Whereas the second is a recursive system described by equation y of n equal to minus a1 into y of n minus 1 plus v of n. If we interchange the order of the cascaded LTI systems, the overall system response remains the same. Thus, if we interchange the order of the recursive and non-recursive systems, we obtain an alternative structure for the realization of the system. Steps in converting from the direct form 1 realization is shown in the following figure A, which represents to the direct form 2 realization in figure C. The resulting system is shown in figure B. From this figure, we obtain two difference equations. W of n equal to a1 into w of n minus 1 plus x of n. Y of n equal to b naught into w of n plus b1 into w of n minus 1. The two difference equations are equivalent to the single difference equation, equation number 1. In contrast to the direct form 1 structure, the realization requiring only one delay for the auxiliary quantity W of n and more efficient in terms of memory requirements is called the direct form 2 structure and is used extensively in practical applications. These structures can be generalized by the general LTI recursive system is described by difference equation. Y of n equal to minus summation k equal to 1 to capital N ak into y of n minus k plus summation k equal to 0 to capital M bk into x of n minus k. Figure direct form 1 structure of the system. A direct form 1 structure requires capital M plus capital N delays and capital N plus capital M plus 1 multiplication. It can be viewed as the cascade of a non-recursive system. V of n equal to summation k equal to 0 to capital M bk into x of n minus k, and a recursive system y of n equal to minus summation k equal to 1 to capital N ak into y of n minus k plus v of n. Reversing the order of these two systems, we obtain direct form 2 structure when capital N greater than capital M. This structure is the cascade of a recursive system. W of n equal to minus summation k equal to 1 to capital N ak into w of n minus k plus x of n, followed by a non-recursive system. Y of n equal to summation k equal to 0 to capital M bk into w of n minus k. The direct form 2 structure requires capital M plus capital N plus 1 multiplications and maximum of capital M comma capital N delays because it requires the minimum number of delays for the realization of the system. This is called a canonic form. Direct form 2 structure for the system is illustrated below. The input-output relationship for the system reduces to below non-recursive LTI system when the system parameters ak equal to 0, where k equal to 1, etc. capital N. Y of n equal to summation k equal to 0 to capital M bk into x of n minus k. The system views only the most recent capital M plus 1 input signal samples and prior to addition weights each sample by the appropriate coefficient bk from the set bk. The system output is basically a weighted moving average of the input signal, which is sometimes called a moving average MA system. Such a system is an FIR system with an impulse response h of k equal to the coefficient bk. That is, h of k equal to bk when 0 less than or equal to k less than or equal to capital M, 0 otherwise. Set capital M equal to 0, the general LTI system reduces to a purely recursive system described by y of n equal to minus summation k equal to 1 to capital N ak into y of n minus k plus b naught into x of n. LTI systems described by a second order difference equations are an important subclass of the most general systems. Structures for the realization of second order systems is shown below. A represents general second order system, B represents FIR system, and C represents purely recursive system. The most general second order system is described by the difference equation. Y of n equal to minus a1 into y of n minus 1 minus a2 into y of n minus 2 plus b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 by setting capital N equal to 2 and capital M equal to 2. If we set a1 equal to a2 equal to 0, then we get a special case of FIR system. Y of n equal to b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2. If we set b1 equal to b2 equal to 0, we obtain the purely recursive second order system y of n equal to minus a1 into y of n minus 1 minus a2 into y of n minus 2 plus b naught into x of n. Recursive and non-recursive realizations of FIR systems. A casual recursive system is described by an input-output equation of the form y of n equal to f of y of n minus 1, comma, y of n minus capital N, comma, x of n, comma, etc. x of n minus capital M. For a linear time invariant system, specifically by the difference equation y of n equal to minus summation k equal to 1 to capital N ak into y of n minus k plus summation k equal to 0 to capital M bk into x of n minus k. On the other hand, casual non-recursive systems do not depend on past values of the output and hence are described by an input-output equation of the form y of n equal to f of x of n, comma, x of n minus 1, comma, etc. x of n minus capital M. FIR systems can be realized non-recursively with ak equal to 0 where k equal to 1 to etc. capital N. Y of n equal to summation k equal to 0 to capital M bk into x of n minus k. FIR systems can also be realized recursively. Suppose we have an FIR system of the form y of n equal to 1 divided by capital M plus 1 summation k equal to 0 to capital M x of n minus k. For computing the moving average of a signal x of n, the system is FIR with impulse response h of n equal to 1 divided by capital M plus 1 for 0 less than or equal to n less than or equal to capital M. Non-recursive realization of an FIR moving average system is shown below. Below FIR system, y of n equal to 1 divided by capital M plus 1 into summation k equal to 0 to capital M x of n minus k is expressed as y of n equal to 1 divided by capital M plus 1 into summation k equal to 0 to capital M x of n minus 1 minus k plus 1 divided by m plus 1 into x of n minus x of n minus 1 minus capital M equal to y of n minus 1 plus 1 divided by capital M plus 1 into x of n minus x of n minus 1 minus capital M. FIR and IIR are general characteristics that distinguish a type of LTI system, and recursive and non-recursive are descriptions of the structures for realizing or implementing system. Recursive realization of an FIR moving average system is shown below. Conclusion. In this chapter, we have covered the following in detail: discrete time signals, discrete time systems, analysis of discrete time LTI systems, discrete time systems described by differential equations, implementation of discrete time systems, correlation of discrete time systems,